Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to talk about section 11.1, sequences. This will be the only section in chapter 11 where we really dive into sequences. What we're more going to discuss in this chapter is series, which is going to be what happens when we sum these sequences. But this hopefully should be a little bit of a review of what you've seen with sequences in the past, or what you already know about a sequence. A sequence is just a list of values in some defined order. We typically will refer to a sequence as this curly parentheses a sub n value, which means that you have a sub 1, followed by a sub 2, a sub 3, a sub 4, etc., up to a sub n. That's what we mean by a sequence, and sometimes that sequence will go up to infinity. So if you do not see some bound on it explicitly, then assume that it does. Assume that it's an infinite sequence defined by some value. Now, what we're first going to try to do is always try to come up with a defined formula that can establish all the numbers in the sequence. If we could do that, it's a lot easier to work with them. We don't want something recursive like the Fibonacci sequence if we can avoid it. For example, I have a couple here. I have 1, 3, 6, 10, 15, 21, 28. This is a relatively famous sequence. This is what happens when you take n times n plus 1 and divide that by 2. That's what this sequence is defined by. Whereas the second sequence I have here, I see 1, 2, 1/3, 4, 1/5, 6, 1/7, 8. This looks like a lot of fractions every other time except for 1, but you can write 1 as 1 over 1. And then it starts to fit that pattern. What we see then with that pattern is that this is just the first number, the second number, the third number, the fourth number, the fifth, sixth, seventh, eighth. They're just using that number either as its whole or they're taking it to an exponent and flipping it over a fraction. So what this is going to look like, it's going to take that number n, and then it's going to take that to the negative 1 power, but not every time. It's going to only do that on the odd circumstances. So if we take negative 1 to the n itself, then that way when we take n and n being an odd number, it'll then take it to the negative 1 exponent. But if n is an even number, negative 1 to an even amount will give you a positive 1 as a result. So you would just get the integer form of that value. So those are just a couple examples of sequences and trying to create a formula for it. Here, I have an example of finding a formula for a general term a sub n in the following sequence. Now I recommend pausing and seeing if you can find out on your own what would be the general term or the formula for this one, because this one really isn't too bad. It should work a lot like the previous one I just talked about. Okay, hopefully you took some time and tried this on your own. This one, again, we see on every other time there's a negative 1. So that means I'm probably going to have, as a sub n, I'm probably going to have a negative 1 to some power here. Since I see it on every odd circumstance, where this is going to be the first, the second, third, fourth, fifth, I see it every time that there is an odd number in the sequence. Then if I take that to the n power, that will always result in a negative 1 on every odd value. If n is even, then it'll be a positive 1. For the rest of it, I see the rest of them are fractions. Thankfully, I see the numerator has a 1, a 2, a 3, a 4, a 5, so it looks like the numerator is just made up by n itself. That's relatively easy, but the bottom is a little bit more difficult. The bottom, particularly after the first one, because the first one can be kind of hard to see, but the second one I see 3, 5, 7, 9, so these are all just the odd numbers. The way that I can define an odd number is usually by doing either 2n plus 1, that's typically how you define an odd number, or what I see here, if I try to plug in 2 there, 2 times 2 plus 1 will give me 5, what I'm actually going to do is go down. So I'm actually going to do 2n minus 1, would result in all these values on the bottom. This works really well for all these fractions following, but I also need to check that first value because it seems off, so it's not a fraction. But if I plug 1 into here, negative 1 to the 1 power is negative 1, and then I have 1 over 2 times 1 minus 1, which is 1 over 1. So I just get an overall value of negative 1, which is what I wanted. So this would be the general formula for that sequence. Usually, creating this takes a little bit of exploration. You might not get it initially, but test some things out, and you should always be able to check by plugging in values to see if you got the right sequence or not. Now, if we can define an equation like this, it'll be a lot easier to work with, because what we're also going to do with these sequences is see if they converge to something. For example, here I saw these kept bouncing back and forth between negatives, but I see -1 2/3, -3/5, 4/7, -5/9, etc. I'm not sure if this is going to any particular number or not. For example, perhaps this is going to 1, or maybe it's going to 0. It's going to actually neither of them. It technically is going to both 1/2 and -1/2, but we'll talk about how we can identify that later. What we're going to do with a lot of these sequences is try to confirm if they are either going to be converging or diverging. Determining whether they're converging or diverging can be very useful for us, particularly in the application of series to come. Sequences themselves aren't as useful, but the series of them, so when we add a lot of the values in a sequence together, then that becomes more interesting. Now, when we talk about a convergent sequence, what we really mean is that the sequence itself is not only getting close to some value, but also that it remains close to that value. So, if I say that a sequence converges to some value overall, then what that would look like on a graph, I would have some points that are going up, maybe they're going down, and they're converging overall to some value. Maybe this value right here. But what it means to stay close to that is that as I go on in the infinity direction, these are getting arbitrarily close to whatever I'm getting, whatever I should be converging to. So I shouldn't just like bounce back up and down around it, but I should get close to that and stay arbitrarily close after some point along the sequence. If I try to define that, what that means is that we say that the sequence converges, and that means that the limit as n goes to infinity of a sub n goes to L, meaning that the sequence itself is approaching some constant value L, which could be positive or negative. This is true as long as if for every epsilon greater than or equal to 0, which means any arbitrarily positive epsilon value, usually we consider a really small value, and this is going to be kind of like a radius, we say. For every arbitrarily small value epsilon, there exists a corresponding value capital N, such that little n greater than big N, which means somewhere along the sequence, if I have the sequence as 1, 2, 3, like the first, second, third, fourth, etc., capital N, etc., little n, basically somewhere along the point of the sequence after that, these values are arbitrarily close to my limits. And for it to be arbitrarily close, that means that the value that you get from the sequence minus the proposed limit of it should be very, very small. We say the absolute value because we don't necessarily care if they're positive or negative. But they should be getting closer to that limit, which means that they're less than some arbitrarily small epsilon value. You could think of this as, let's say if I chose the value epsilon to be just 0.01. Then that means somewhere along the line, the values in my sequence are so close that the distance from my proposed limit value and the values I actually have in the sequence are less than this. So they're less than just 100th away. And then I could choose any other small epsilon value, maybe 0.0001. That means somewhere along the line in the sequence, the values are even closer than that distance away. Another way you can write that with mathematical notation, this is if you're familiar with it, this is read as if for all epsilon greater than or equal to 0, this symbol means for all. So if for all epsilon greater than or equal to 0, there exists a capital N, this backward E means there exists, such that, which we usually reduce down to ST, such that n greater than or equal to n implies this. So the same stuff, just kind of written in more mathematical notation that you'd see further down the road. Now what we're going to do is we're going to show how you can apply this definition for convergent sequences to show that a sequence converges. Moving on after that, we're going to usually use a lot of other theorems and identities to prove something. Something's more, a little bit easier to do than these, which tend to be kind of hard to do directly. Okay, so we have show the following. We have the limits as n approaches infinity of 1 over np equals 0, for p is a positive integer. That's what this means. So this means p is an element of, and this is positive integers. You've probably seen me use that z before. Z typically means positive integers, although it usually looks like this. That means that means integers, and then put a positive sign above it means positive integers themselves. So 1, 2, 3, 4, etc. So what that means is that we're talking about things like 1 over n, or 1 over n squared, or 1 over n cubed, or 1 over n to the fourth. These kind of sequences. If a sequence is defined with this, then this should be approaching 0 as the value for n approaches infinity. Which we kind of should already know this, but we have to confirm it. So to do so, this is how we're going to work about it. This is sometimes called an epsilon proof. What we start off with, the first line of the proof, will say, given arbitrary epsilon, and epsilon can be anything, but we want it to specifically be greater than 0. This way it aligns with the definition of the proof. We are going to choose some n value. And that n value is going to depend on whatever epsilon we chose. However, we don't know what n is going to be yet. We know we want it to be greater than some value, but we don't know this yet. This is actually going to be the last number or last thing you find out in the proof as you work through it. Sometimes you'll see proofs that are already written out, in which this number is already there. However, you usually don't know what that is until you're almost done with the proof. Okay, but for now, we'll figure out what that blank is in a bit, and we'll just say, all right, we're going to choose some n value. Then, by the definition before, what that implies is that n greater than bigger n implies that a sub n less than L, and remember that our goal here is to show that this is less than epsilon. If we can show that, then that means that this is convergent. However, we don't know really what this is yet. Our goal is to get to less than epsilon, but that's going to be later on down the road. So we're going to do some math and hopefully transform this into something that we can confirm is less than epsilon. Well, what we can do for a sub n, we have that defined. This sequence is my a sub n value. So I can simply replace that with 1 over n to the p minus L. And what I'm... well, actually, L we can actually imply as well. L we're assuming is 0. So we're going to say 1 over n to the p minus 0, otherwise known as just 1 over n to the p. We can drop the absolute value because for 1, p is a positive integer, so that's fine, although that wouldn't really matter too much. But n is approaching infinity, so this is going to be an arbitrarily positive integer, or a positive number. Now, again, what we wanted to do originally is have n to be, or capital N to be in terms of epsilon. Right now we have little n, so we need to get little n out of there. We need to change that into capital N. In order to do so, we think about this statement we said, that if I'm talking about some little n that's bigger than that capital N, basically any value past this bound on my sequence, so somewhere along that line of the sequence. If n is bigger than n, then similarly, what that implies is that if I compare 1 over n to the p to 1 over capital N to the p, if little n is larger, that means this one has a larger denominator, which means that it is itself smaller than 1 over capital N to the p. And this, again, we know because n is greater than capital N. Now that we have capital N, and we want to show that this is less than epsilon, now we can come up with a value for capital N. Specifically, what we want to do with capital N is we want to replace it with something so that I get less than epsilon as a result, or even equals epsilon is fine. So what I want to do is get epsilon on top, and I want to get rid of that p exponent, so I'm going to have to do a couple things. So we're going to build something here so I can get rid of epsilon, or you can actually solve this separately. So we want this to be equal to something that's less than epsilon. Or actually that's equal to epsilon is fine as well. So we really want 1 over capital N to the p equals epsilon, and if we want to solve for n, we can flip both sides to get n to the p equals 1 over epsilon. And then you get n by itself by getting 1 over epsilon to the pth root, or the 1 over p power. Then that means when I replace capital N with this, I get 1 over epsilon to the pth power, or pth root to the pth power. Now that I replace that, then I get epsilon, which is less or is greater than my proposed value, which is all I want. And then I have, therefore, little n minus L is indeed less than epsilon. You don't have to have a series of less thans. As long as you just have one in the middle, that means all this stuff is less than all this stuff, which is all we really need. Okay. Now then, we determined how we were going to find n, so now we can say that n is greater than, or maybe even greater than, or equal to the pth root of 1 over epsilon. This is, again, how you would typically see a proof done when it's already constructed. You would see, given arbitrary epsilon greater than or equal to 0, choose n that's greater than this weird manipulation of epsilon, which does not make a lot of sense until you get down to this line. Once you get down to this line where you need to convert capital N into some amount of epsilon, then you can solve for that and come up with that weird manipulation of epsilon. So these proofs kind of work a little bit backward. You move through it, and then you get to a point that you're like, okay, I need to construct how I need capital N to look like in order for this proof to work. So I just need to reorganize some things. But this shows my proof. This is all I really need. And this is going to be something that we can use relatively often. If you ever see a sequence, specifically a sequence of 1 over n to any power, we know that sequence goes to 0. It may be obvious, but we know that for sure now. Okay, so you won't have to do those too often, but it's good to start to get those down, particularly when you eventually run into epsilon and delta proofs later on down the line in algebra and number theory. What we are going to do a lot of with sequences, though, is stuff like L'Hopital's, but we also have a lot of properties of sequences we can use here. Most of these have already been shown before in calculus and other classes, so I'm kind of just summarizing them here. First, limit of a constant k is equal to that constant. Limit of a constant times a sub n, you could pull the constant in front of the limit. Limit of two different sequences, added or subtracted, you could split that into two limits. Same thing with multiplication, same thing with division, as long as the one on the bottom is not equal to 0. And also the limit as the absolute value of a sub n equals 0 means that it's also just equal to 0 itself. This is useful for the ones that approach 0 in this fashion, where they bounce up and down, kind of like a cosine or sine function, but they are getting closer and closer, arbitrarily closer to 0. What that means is that we can just drop the absolute value, which is good, because those are kind of hard to work with. Two of the most important ones from this section, though, that you may not have discussed are 7 and 8. 7 says that if you have the limits of a function is approaching L, and you have that the function of values of n will give you that sequence, meaning that the function itself, maybe this is my function, and it's approaching some limit. If I plug in values of n, if this is n, I plug in values of n, and these values are my sequence, they just follow along the function itself, then that means all I need to do is I just plug in the function of that value of n, and that approaches L. what this means is that I can now relate sequences to just functions themselves. So instead of dealing with, like before, 1 over n to the p as n goes to infinity, what I can do instead is the limit as x approaches infinity of 1 over x to the p and deal with this like I would with functions, which is helpful. And 8 says something similar as well. If you know the limit of a sub n goes to L, then that means if you have those values inside of a function itself, then you can kind of pull the function outside the limit and just say the function of the limit of a sub n, which is just L itself. So then you could just plug in L into that function. Another handy trick that we will sometimes use. So a couple ones to pay attention to. We also have something called the Squeeze Theorem. You may also be familiar with this, but this is helpful for some sequences that aren't as clean to work with. If you can squeeze them, though, between two convergent sequences, then you can confirm that it is convergence. Literally, it is just about squeezing. So if you have maybe a sequence like this, and it's not exactly sure how to work with that algebraically, if you can squeeze that between this convergent sequence and this convergent sequence, both of those going to L, maybe I'll do L in black, so both of those are going to some limits, then that means that you know the sequence defined by these blue dots is also going to that same limit, because you squeeze them between two convergent sequences going to the same place. That sounds more difficult than it is, and I'm going to show you an example of that here in example 3. This one, we just have the limit as n approaches infinity of sine to the third n over n equals 0. Well, if I think about what sine cubed n does, I know what sine of n does, and if I cube that, it still does the same thing. This bounces between -1 and 1 constantly. So what that means is that I know that sine cubed n over n, I know that it is always larger than -1 over n, larger than or equal to, and it's less than or equal to positive 1 over n, because sine cubed n always bounces between -1 and 1. If this was sine squared n, then I could say 0 over n and 1 over n. But since this is cubed n, I know that this bounces between -1n and 1 over n. And well, we know this converges because we just did that. We did, in the previous example, that 1 over n to the p, the limit of that converges. And we also know this converges because if you have a negative, you can pull that in front of the limits, because it's a constant technically, and you're again dealing with 1 over n, which also goes to 0. So therefore, the limit as n approaches infinity of sine cubed n over n approaches 0, because we know that the two functions that squeeze between goes to 0. That's all we need to know. So that's how you would use the squeeze theorem. You won't use it all the time, but it can be helpful for those that you can't solve otherwise or use L'Hopital's with. L'Hopital's will be another common thing to work with on a lot of these. Lastly, another primary concept from this is defining something as a monotonic sequence and using the monotonic sequence theorem. Okay, to do the monotonic sequence theorem, you're actually trying to show two things. You're trying to show that a sequence is bounded and that it's monotonic. If you can show that something is bounded and monotonic, then that means that it is going to be convergent, which is pretty nice, because showing something is bounded and monotonic is not that hard. Bounded just means that there's some value in which all the numbers in your sequence are less than that. You don't really need to choose a value that's like right at the cusp of it or what it's approaching. You just need to find some value. For example, I know if I have maybe the limits of b sub n, and I know that b sub n is bounded above by 100, then I'm good. If it's bounded above by 100, that means it doesn't go above 100. But that means it also doesn't go above 1,000 or 10,000. All those would be fine. Those all define that it is bounded by some constant value above. And this would be helpful for me to show that it is converging to some positive value. So bounding really is not the difficult part of this, and this definition here shows what bounding means. Sequence is bounded above if there exists u, which typically means an upper bound, such that all the values of your sequence are less than that, or less than or equal to it, for all n greater than or equal to 1. And then it's bounded below if there exists a lower bound L, such that all the values in your sequence are above something. So this is useful for if you're trying to show that a sequence is converging like this, or if a sequence is converging like this. If it's going up to some value or down to some value. Either way, finding something to be bounded is not that hard. Just work with the actual definition of the sequence and you should be fine. The more difficult thing is showing that something is monotonic. Now, what we mean by monotonic is either non-increasing or non-decreasing. So monotonic means that the sequence is non-increasing or non-decreasing over the interval of n greater than or equal to 1. So over the values in the sequence. Now, the book says that it's either increasing or decreasing. That's what monotonic means according to the book. However, that's not what we need. And increasing or decreasing is actually a very, very strict condition. Non-increasing or non-decreasing is much more lax. When something is non-increasing or non-decreasing, if it's non-increasing, then that means that when I go from one value to the next in the sequence, it's not going up at all. But that means it could stay constant for some time. That would imply that it's not increasing at all. If I say that something is strictly decreasing, then that means as I go from one value to the next, it always has to decrease in some manner. But if I only talk about the decreasing sequences, that loses out on those that sometimes stay constant because those also can be convergent. So what we're going to show is just that something is non-increasing or non-decreasing. We say a sequence is non-decreasing if a sub n is less than the next value. So if some value in the sequence is less than some other value in the next sequence, less than or equal to. The equal to is what makes it non-increasing. If you had strictly less than, then that means that this would be an increasing sequence. If you can show it's increasing or decreasing, though, strictly, then that also works. But non-increasing and non-decreasing is a little bit more lenient. Non-increasing means that all the values, some value in your sequence, the previous one is always bigger than the next one, or bigger than or equal to. That means it's not increasing. An example of a non-decreasing sequence we had above here in this paragraph, I have, for example, 1, 2, 3, 4, 5. That would be considered an increasing sequence because every value is always increasing from the next. But the next one I have, 1, 1, 2, 2, 3, 4, 5. This would not be considered increasing because I have intervals here where they stay constant at some point. However, both of these would be considered non-decreasing because they do not decrease at all from one value to the next. So that's why non-decreasing is a better term to use. If we could show that a sequence is both bounded and monotonic, then that means it is then that means it is a convergent sequence by the monotonic sequence theorem. So if it's bounded and it's monotonic, then that means it's convergent. Now that may sound confusing, but we're going to do a couple examples to help alleviate that. But one last note before I go into it. All of these always have n greater than or equal to 1 in them. However, it's a little bit more lax than that. If you find that the first maybe 5 values are increasing and the rest of them are non-increasing, then you can show that the rest of the sequence is convergent after some point. It's really talking about if it's converging in the infinite sense. It doesn't need to be converging or diverging in the finite sense. So if it's doing some weird stuff for the first 10 values, but then it's converging to something, or maybe it's diverging to something, then you can just work with those values instead. So really, n greater than or equal to some value later on in the sequence is a little bit better way to think about it. But let's do a couple examples so you can see how these would be done. Okay, so here we're going to determine if the sequence defined by the following is either convergent or divergent. The first thing we really want to do is plug in some values for n and see what we can get. So if I start defining some of these values, so a sub n, if I start off with 1 to the second power over 2 to the 1, I get 1 over 2. If I plug in 2, I get 2 squared, which is 4, over 2 squared, which is also 4, so I get an overall value of 1. If I plug in 3, I get 9 over 8. So far it looks like it's increasing. But if I start to plug in more, if I plug in 4, for example, I get 16 over 16, I'm back down to 1. If I plug in 5, I get 25 over 32. And 6 will give me 36 over 64. 7 will give me 49 over 128, etc., etc. You'll start to see that the denominator here is growing at a much faster rate than the numerator. And looking at the things that lead to that, n squared is going to be the same exponent, but the bottom is going to have an increasing exponent constantly, which means that it's going to get larger and larger a lot faster. However, what we see here, like I was talking about, the first 3 terms are increasing, or they're non-decreasing. But the rest of those after that, or you you can even say from 9/8 and on, the rest of these are decreasing, or better way of saying that is non-increasing. And we show that that is happening not after the first, the second, but from the third number beyond. Okay. If you don't want to explore it that way, you can also explore algebraically if you so please. If we look at a sub n compared to a sub n plus 1, so the next one, what we want to show for something to be non-increasing is we want a sub n to be greater than or equal to a sub n plus 1. This is what is going to show non-increasing. We kind of get that from testing some numbers. If we plug things in, a sub n being n squared over 2 to the n, greater than or equal to a sub n plus 1, we get n plus 1 quantity squared over 2 to the n plus 1. Now we have an inequality here, which means we can maneuver things to either side. If I multiply the 2n plus 1 to the other side, and I divide the n squared over, or really if I just move the 2n plus 1 to the other side, that's going to cancel out that 2n, and I'm going to have a 2 left over. I'll get 2n squared is greater than or equal to n plus 1 squared. Expand that out. That gives me n squared plus 2n plus 1. And then I can subtract away, move an n squared over and the plus 2n, and we get n squared minus 2n is greater than or equal to 1, so a constant so I can compare to. And I have n times n minus 2, which is this factor, is greater than or equal to 1. This is only true when n is greater than or equal to 3. If n was 2, then I have 2 times 0 is not greater than or equal to 1. If n is 1, I have 1 times negative 1 is not greater than or equal to 1. But if n is 3, I have 3 times 3 minus 2 is 1, so 3 times 1 is greater than or equal to 1. So it's only true for values greater than or equal to 3. So that's another way of showing that it is non-increasing. So, non-increasing, done. The second thing we need to do is we need to show that it is bounded. We can do these in either order, really. Looking at these, though, we're trying to show that it is non-increasing, so it's going down to something. Well, pretty easily, I could say that it's bounded by 0. So since the numerator and the denominator are always positive, a sub n is always going to be greater than or equal to 0. So it is bounded below by 0. Done. And with that, we know that it is convergent. We know that this is convergent because it is non-increasing and it is bounded. If you actually put this into a limit and solve with L'Hopital's, you'll actually also find that limit. You'll find that that limit goes to 0. Because the derivative of the top twice will eventually go away, but when you take the derivative of the bottom, that will never go away. You'll just have some natural log of 2 stacking up. So that'd be an example of determining that it is convergent or divergent using the previous theorem, the monotonic sequence theorem. Now, if you have the equation like that, again, we could have also done this by doing L'Hopital's or something, trying to find what this limit actually is, if possible. But if you don't have the defined sequence like this, if you have something like this, which is recursive, it's a lot harder to do that. But we still want to show that it's increasing and bounded in order, and we want to be able to show both of those. So what we're actually going to do in order to solve this is use the process of induction. Induction is something that you may have seen in a previous class, and if not, it'll be a very useful tool for proofs. Inductions are basically the best proofs to do if you're just starting out because they're the simplest to do. They follow a strict regimen every time, and you just follow through with those and get done near the end. And there's no like exploring really here. It's just a little bit of algebra maybe. Induction itself has 3 steps, sometimes 4 depending on who you talk to, but 3 primary ones. First, you want to show that n equals 0 is true. So basically, or n equals 1 is true, I guess I'll say. So n equals 1 is true. Which basically means you just want to show that whatever you want to try to find is true for the first case. So for whatever the first number is in the sequence, we're going to show that it's true. Either that it's convergent, or either that it's bounded, or either that it is monotonic. Then you want to assume true for n is equal to k. Basically, you want to assume that it is true for some value later on down in the sequence. Then show it is true for n equals k plus 1. That is induction. Those are the 3 steps of induction. What this does is it shows that it's true for any finite number you could choose, including the first one is the easiest. And then if you could show that it's true for, if you assume that it's true for k, which k could be 1, for example, you showing that it's true for the next value in the sequence will help solve for everything else. Because that's kind of the hard part with proofs when you have an infinite amount of values here. If you do it like this actually does prove for all infinite values of n, because you have it true for some finite value of n, and then every value past that. So the k plus 1 clause will help you solve that it's true for 2. That'll then solve that it's true for 3, and then 4, and then 5. It'll keep expanding. So these are the only 3 steps that we need to show for induction to show that whatever concept is true about something. Alright, so we're going to do that with both of these. Now, first what we can do is show that it's increasing. Increasing might be the easier one, or non-decreasing. So, increasing or non-decreasing. Okay, now to show that it's increasing or non-decreasing, for the first step, we want to show it's true. So show true for n equals 1. Remember that what it means to be increasing or non-decreasing, again, we got the implication of increasing because we got a plus here, so it looks like it's going to be increasing. But if we're trying to show that it's true for n equals 1, non-decreasing means that a sub n is going to be less than or equal to the next value in the sequence. So whatever value I have is always going to be less than or equal to the next one. If that's true for 1, then we want to show that a sub 1 is less than a sub 2. And thankfully, we can easily do that. We have a sub 1 is 3. A sub 2, if we just plug in here, a sub 2 would be the square root of 3 plus the previous value in the sequence, which is the square root of 3. This is true. So we're done. That's it for the first step. Root 3 is for sure less than square root of 3 plus root 3, all under the root. That's it for the first step. So we know that it's true for the first case at least. Now what we're going to say is assume true for n equals k, which means that we want to assume that a sub k is less than or equal to a sub k plus 1. So we're going to assume that is true. Sometimes this is called an induction step. And it's going to be called an induction step because we tend to use that when we go back and prove everything. So we're going to use that and maybe the first one to help show this next one that that we want to show that it's true for n equals k plus 1. So that means we want a k plus 1 is less than or equal to a k plus 2. That would be that case. Again, all this is coming from the fact that this is what it means to be non-decreasing. Now, this may sound difficult, but it's not going to be. If we just plug in what this would mean from the original equation, a sub k plus 1 would imply that a sub k plus 1 is equal to 3 plus a sub k. And a sub k plus 2 would mean that this is 3 plus a sub k plus 1, the previous one. If we square both sides, we get 3 plus a sub k is less than or equal to 3 plus a sub k plus 1. And then if we subtract 3 from both sides, we have a sub k is less than a sub k plus 1, which is true. And we know this is true from step 2. Step 2, our induction step, said that we assume that this is true. Therefore, since we know that this is true and we got that conclusion to show up again, then that means that 3 was true. So basically what we've shown is that this is true for the first case and then any case following that. It's true for all infinite values following that. So we have that this sequence is monotonic. Now, I did it with non-decreasing. You could have also made it more strict and just did increasing. So a sub n is less than a sub n plus 1. Would still work perfectly fine. But again, that's half of it. We have monotonic. So we need, again, first we want it to be bounded. And we want it to be monotonic. So we're done with the second one. Bounded is going to take another induction like this. So for bounded, we did monotonic. Now for bounded. Again, we're going to do all 3 steps. We're going to show true for n equals 1. Well, the question is, what are we going to make it bounded by? If we start testing these values, maybe we can find one out. We have root 3. That's going to be less than 2. Then root 3 plus root 3, I think that's around 2-ish. And if you keep testing these values, you can find some value to test it by. You can find a really clean one, or you can make one that's really nice for you. For example, how about I say bounded by 10? Why not? 10 seems like a good enough number. I think 2.5 would work as well if you test enough for that. Maybe even 3 if you just want to use 3. But again, we don't need to be too strict by this. As long as we show that it's bounded by something above, some whole number, then we're fine. And so again, we're going to have to show this with induction. So first, let's show that it's bounded by 10. For n equals 1, the first value we have, a sub 1 equals root 3. Is that less than 10? Yes, it is. So it's good. That's all we need for that. Now we're going to assume true for n equals k, which means that some value later on in the sequence, we want to show that that is less than 10. You can even say less than or equal to if you wanted to. So we're going to assume that this is true, and hopefully we can use this later on for our third step, where we show true for n equals k plus 1. Well, if we have a sub k plus 1 from the original formula given at the top of this page here, the square root of 3 plus, or a sub n plus 1 equals square root of 3 plus a sub n. If I have a sub k plus 1, this is equal to the square root of 3 plus a sub k. Alright. Now, if I'm trying to solve for this, I want to hopefully be able to use my induction step from before to help show that this is also less than or equal to 10. Well, here's an easy way to do that. If we assume that a sub k is less than or equal to 10, let's just use it as 10 then. At most, this would have to be less than 3 plus an a sub k plus a sub k. Let's just say it's 10. Why not? If that's the biggest that it can be, then likewise a sub k plus 1 has to be less than or equal to this. Could be equal to if a sub k is equal to 10, but it could be less than that if a sub k was less than 10. Well, what we have now is square root of 13. And the square root of 13 is itself less than or equal to 10, because it's less than the square root of 100. So, done. So, this sequence is bounded. That's all we need. We showed it's true for the first one, came up with an arbitrary number. Again, you can test some values to get this. You can come up with your own or something like that. It's usually good to just test some if you're not sure what the sequence looks like. But I just came up with 10 because it seems like a good number to work with. I could have done this exact problem with 100. Less than 100. This being less than 100. Okay, put in 100. I get this square root of 103. That's less than 100, so we're good. Could have really chosen any number that's above whatever it goes to, whatever the limit is. Notice I didn't even solve for what the limit is. I don't know what it is. All I know is that it does exist, because we have now that it is bounded and monotonic, so this is convergent. As long as I have those two things, that's all I need. Okay. Induction is a nice thing to learn and work with proofs. If you can do an induction, it is relatively handy because it does just follow those 3 steps. And it is relatively algebraic in nature. There's not too much exploratory concepts there or citing a lot of previous theorems to do stuff. The most you're citing is your step 2 to get to everything else. All right. So that's it for this section, for 11.1. Again, what this is going to lead into is a much bigger topic for series, where we're going to talk about what happens when you add the values in these sequences. If you have any questions, though, feel free to put those in the comments below or ask your instructor directly. I hope you have a nice day.